Okay, it's 5:25, so let's get started. Just a few brief announcements. Recitations start tomorrow. They didn't start on Tuesday because of Independence Day, so I hope everyone had a good Independence Day. But they will start on Thursday, and Andrew will be running them. Problem set 1 is out, so should you have started it, or should you start it on Monday? When is problem set 1 due?
Next Tuesday.
Wednesday or Tuesday?
Tuesday. Definitely Tuesday.
Tuesday. You should know that. Okay? And now we come to problem set 0. So why is it so hard? It's all prereq material. So what I was planning to do was I was going to extend it to tomorrow. But here's the thing. Only 3 people have come to Dylan's to his office hours, both of his office hours in total. And only 20 people came to the extra help session this past Monday. And there's still 5 people who haven't signed up on Piazza, and there's still several people who haven't even accessed the Blackboard site. So what should I do?
You should not punish the whole class. It's not going to help you make sense.
Well, what do you think you should do from now on? Start early and ask questions and work hard. Yeah, go ahead.
I feel like that's a bit of a misnomer. I started the day it came out, and I've been emailing you constantly.
Yeah. Mm-hmm.
I still don't have it done.
Yeah, there are several people who have been working really hard, and I'm very happy about that, but it's only a few people. So what should I do? I have a strategy, but if you're willing to work hard and promise me you'll work hard, I will meet you halfway. How does that sound? I will come back to this original policy, the policy statement of syllabus, if people don't work hard, okay? So if you're willing to work hard and actually participate on Piazza, come to the extra help sessions, I'm absolutely willing to meet you halfway. People willing to work hard?
Yeah.
So here's the strategy we'll take. So we'll take the maximum of these 2 options. So you will always have the highest grade. So the raw total as before. So is either your grade's going to be either exactly as before or the maximum of that and the following. The nice thing about GradeScope is that we have access to the individual problem scores. Instead of just the entire problem set score that you get, I have access to the original problem set scores. So how many problem sets are there in total? 6. Because we started at 0, we end at 5. So 6 problem sets. There are 5 non-bonus problems on every problem set. So how many non-bonus problems in total? 30. So what I'm going to do is take the top 25 out of 30. Non-bonus problems. Got really quiet. Scale up to 300 points. So it'll be out of 250 for the non-bonus problems. And I'll scale whatever that is to 300 and add any bonus points after. So I will go back to the original policy if people don't work hard. If I've determined people don't go to recitations, don't come to the extra help sessions, don't ask questions over email and Piazza. But if people do work hard, I will use this strategy. Yeah.
The top 25 meaning the most answered correctly?
The highest scored. Yeah, highest scored. Yeah. I'll drop the lowest 5 for that.
Per individual, right? Not like
Yeah, per individual. Yeah. Yep. Yeah, so it's individually calculated. Yeah.
So this is great in grade, but understanding will be solutions that are understanding problems.
Every single graded piece of work except the final exam for ASU reasons will have solutions. Everyone. And it'll have a rubric detailing exactly how it was graded, and multiple solutions if there are multiple solutions. Okay? Yeah.
Will we have access to the solutions for the first or the second problem set before the exam? I figured that's what a student did before.
I'll try to prod Dylan and tell him,
Okay.
get them done early. But yeah. So for problem set 1 is due Tuesday, midnight, and your exam, first midterm exam, is on Wednesday. Yeah. And as I detailed in the announcement, there are 165 points available out of 150. And you will, if you happen to earn more, you will keep them as bonus credit. Okay? So I am trying to help here, but I can only meet you halfway. And you have to meet me halfway. Okay? Sounds good?
Yeah.
Any questions otherwise?
So is problem 0 still due tonight?
It's still due tonight. Unless you can make an argument as to why I should move it. And tell the grader, I'm going to mess up your schedule and we're going to make you start grading 1 day later.
I think part of the question over here was, will the answer sets have explanations or will it just be a solution?
We'll try to make a good enough explanation, yeah. Yeah, but remember, this is prerequisite stuff and standard problems. So they're not totally out of the blue problems.
So you said that problems that you're based on the prerequisite material,
Mhm.
but it seems like a lot of us are struggling.
Yep.
What should we do to fill in that gap?
Chapter 0 of SIPSR, which has everything in MAT 243 that you'll ever need. 310, what are the algorithm design paradigms? Greedy and what? Starts 2 words. Starts with dynamic and ends with programming. Okay? One of those will help you. Okay? Other questions? I think this is a good scheme. Any other things? Notice how many empty seats there are. There are some people who don't take the class seriously, so if the majority of the class takes it seriously, I will follow this. Okay? But any other last minute things? Okay, so on Monday, let's recap. What did we talk about on Monday? Yeah, these things called NFAs, nondeterministic finite automata. And what were so why did we even come up with this thing called an NFA? Solve this problem of concatenation. And we saw that it was a problem with DFAs because, first of all, we couldn't decide whether there was such a split of the strings into 2 parts, such that the first language has the first part and the second language has the second part. But even if we knew how that was, for some strings, we might not know that for every single string. So we introduced this idea of non-determinism to let us choose to start reading the second part, non-deterministically. So it's kind of this magic black box that helps us try to compute something that is that seems hard for deterministic machines, but is really, really easy for non-deterministic machines. So that's where we left off last time. Well, what did we show? We didn't show that the class of regular languages are closed under concatenation. We showed that the class of languages recognized by NFAs are closed under concatenation. We didn't establish equivalence of NFAs and DFAs yet, which is what we're going to do now. But if I show you how to show that DFAs and NFAs recognize exactly the same languages, then we know that the class of regular languages are closed under concatenation and star. Okay? So if I want to establish equivalence between NFAs and DFAs, what do I need to do, or what do we need to do? Yeah, so that's one direction. I need to show you how to convert any DFA into an NFA. And what else do I need to show? And every NFA to a DFA. Okay, so let's do one direction first. Oh no, not that direction, the other direction. That direction's a lot harder. as we'll soon see. So what I want to claim is that every regular language can be recognized by an NFA. If I say every regular language, what should you know immediately? There's a DFA for it. So if I can convert any DFA into an NFA that has exactly the same language, are we good on this part of the proof? It's not a rhetorical question. Yeah. So if I can convert an arbitrary DFA into an actual NFA that has exactly the same language, then we're all good for this part. Any ideas?
Well, the problem that you're going to start running into is the epsilon transitions.
We're not doing that side yet.
Oh,
We're doing converting DFA to NFA. Wait, can every NFA do what a DFA can?
Yeah. And
So isn't this seem like really immediate? Like this seems pretty obvious. It does seem pretty obvious, but there's one catch. So state diagram of a DFA is already an NFA. Because there's nothing in the NFA definition that says you must use epsilon transitions or you must use multiple transitions on the same symbol. A DFA already is an NFA in the sense of the state diagram of a DFA is exactly is already an NFA. So why can I not immediately say yes that this is true? What is different here in the NFA world that's different than the DFA world? Yeah. Yeah, so what's the difference between the transition function?
The DFA is between states.
DFA is to, so the DFA goes to how many states? Exactly one, right? And NFA goes to a element of the power set, which is just a set of states. It's just a set of states. Oh, so what can we do here? So if M, so this thing is a DFA, we make an NFA, I'm going to call it N instead of M. Well, since we have this idea of not modifying the state diagram, I think most of this stays the same, except for the transition function. So I'm going to put delta prime on that guy. Oh no, the start state is the same. And everything else is the same because we didn't modify the state diagram. But what should the transition function do? Well, the transition function of an NFA takes what two things as an argument? It takes a state and a input symbol or epsilon. When I have this DFA, does that have any epsilon transitions? No, so I don't even need to worry about those. So we know that delta prime will take a state and an input symbol. But what is the output of an NFA's transition function? A set of states. So I gotta put a set of states. But since the original thing was a DFA, how many things will be in this set? A single element, because there's exactly one state I went to before. So the set of possible states I can go to in the NFA is the one state. So I need to write one state here. And then I gotta say if in the original DFA, the transition was Oh, not A. Should be Q prime. So if in the DFA I had a transition from Q to Q prime on the symbol A, then in the NFA, I'm going to have Q on input A go to the set, which has only Q prime in it. Okay? But the computation works exactly the same, because if we just follow the same sequence of states, because I didn't change the states or any of the transitions, other than the fact that it's a set now, then we get the language of the original DFA-M is exactly the same as the language of the NFA-N. So L of M equals L of N. QED. All right. Yeah.
Can you explain the last two lines you wrote really quick, starting with
Yeah.
the delta prime?
Of course. So when we talked about DFAs versus NFAs, the DFA transition function only outputs a single state, whereas an NFA outputs a set of states. Is a single state equal to a set of states? No, those are completely different things. So we needed a little bit of work to say that the NFA will do exactly the same arrow transitions, but instead of going to a single state, it will go to a set of states, which is the original state that the DFA went to. So it's just for formality reasons. But in terms of the state diagram, everything is exactly the same. Okay? Any questions on that? Yeah.
This might seem like a silly question, but the set of states that are output by an NFA, those are all the possible places it could go, right? Am I understanding that
Yeah.
correctly?
So remember that an NFA takes in a state and input symbol or epsilon, and it outputs a set of possible states it can go to.
Okay, great.
Yeah. Yeah. So here, Q prime, the set containing Q prime, is the only state that it could possibly go to. Okay? But any other questions? Well, we proved one direction, which says that every DFA can be converted into an NFA. What's the other direction? Every NFA can be converted into a DFA. But think about what that says for a second. That says that this NFA, arbitrary NFA, with these epsilon transitions and maybe missing transitions and maybe multiple transitions on the same symbol, can be converted into a DFA, which has none of those things. That's what that's saying, right? So what I want to do is go over a little example of what we might do. And then we'll actually give a formal proof of it. So let's say we have this NFA. So this is an example. Thank you. Yeah, pretty much every example I use in this class I make up on the spot, including this one. So this is an NFA. I hope we can agree on that. Is this an NFA?
Yes.
Yeah, because as epsilon transitions and single symbols, A and B, yeah, there's nothing wrong with this NFA here. Well, let's try to think about what we would do if we just thought about an equivalent DFA for this. I don't know what language it is because I just made it up. But even if I knew what language it is, I need some algorithmic way of converting any NFA into an equivalent DFA. Do DFAs have epsilon transitions? No. Well, so what I think I need to do for the DFA is that the start state obviously can't have epsilon transitions coming out of it in the DFA. An NFA certainly can, and in this case it does. So we need to think about what we could do. Well, think about if you were trying to run this NFA. before you read any input, what possible states could you be in? Q0 or Q1? I could be in both, right? Why? Because of the epsilon transitions, right? Before I read any possible input. So maybe what I could do is, let's model that particular set of possibilities as a state in a DFA. Okay? Let's see. So if I modeled this as the set which has Q0 and Q1, and modeled that as the state, the start state of the DFA that I'm going to make, that gives us some progress because this says that these are the possible states you could be in if you were running the original NFA. Okay? Because the NFA could make a choice as to which state it's going to be in. Okay, well, can I get anywhere else on epsilon transitions from either Q0 or Q1 to some other state? No. So those are the only possible states I could be in before I've read anything. Okay. Well, it's the transition function of a DFA total. Yeah, so what does that mean? Yeah, every state of the DFA has a transition. Well, let's say the alphabet is A, B here. Has a transition on A and another transition on B somewhere. So we got to figure out, where does this guy go on A and where does this guy go on B? These may be self loops, I don't know. But let's just see what happens. Well, let's see. I could be in Q0 or Q1. Where can Q0 go on the symbol A? Nowhere. So let's just forget about that for now then. Q1 on A, where could I go? Q3 or Q2 because that's what the transition function said to do. So let's start writing down the possibilities. Can I get anywhere else on the symbol A? From a Q1, I mean. No. So let's think about now. Since the DFA has no epsilon transitions, and the NFA does, do I need to check whether I can go to somewhere else from Q2 or Q3 via epsilon transitions? Yeah, I need to keep track of that. So, can I get anywhere else other than 2 or 3? No. So now let's model that as a state. Okay? Q0 or Q1 on B. Can Q0 go anywhere on B? No. Q1 on B anywhere? No. Oh, wait. I'm going to a set of states, but I can't go anywhere now. So what set is the set of states I'm going to? Empty set, which is the set which happens to have no states. I can't go to any of the states. So I'm going to make a state which is called the empty set. No prejudice against the empty set here. It's a perfectly good name of a state. Let's do 2 more sets of transitions. Let's do the empty set. If I'm nowhere right now, which is what empty set means, where can I go on the symbol A from nowhere? Nowhere. But now we gotta check again if we can go to somewhere else via epsilon transitions. Can I go from nowhere via epsilon transitions to anywhere? No. So, empty set on symbol A, where does it go? To itself. And I think that's the same is true for the symbol B. Sweet. So now let's do Q2, Q3 and see where it goes on the symbol A and B. Q2 on A, where can I go? I can't go anywhere. Q3, where can I go on A? Nowhere. Oh, what is this nowhere? Empty set. Can I go anywhere via epsilon transitions somewhere else from the empty set? No. And oh, do we already have a state for the empty set? Yeah, we just made it. So I'm going to have a transition from 2 and 3 on the symbol A there. let's do this one and then we'll try to generalize this. Q2 and Q3. Can Q2 go anywhere on the symbol B? Yep. It can go to what? Itself and 0. So let's start writing down the possibilities. 0 and 2. Can Q3 go anywhere on the symbol B? No. So I'm going to ignore that now. Can I get anywhere else via epsilon transitions? Well, can Q0 go to anywhere via epsilon transitions? Yep, Q1, so I'm going to write it on my list of states. And nowhere else. Can Q2 go anywhere via epsilon transitions? Q3. And since that's all the states, I'm going to make that a state. Okay? Yeah. Which one?
From Q2, Q3, like following A, you can't go anywhere. You can go to Q3,
So here we're fixing the states. So like in the upper right state, Q2, Q3, we're fixing 2 and 3 right now. We figure out where we could go on the symbol A. Then from wherever we just written down, we figure out where else could we go via epsilon transitions. Yeah, good question though. Any other questions? Yeah.
I'm kind of confused on the notion of going nowhere though. Like I understand we can go to the empty set, but what would that actually mean?
So so it kind of means a dead state. So this empty set with self loops and it's not a final state, that's usually called a dead state, or some people are nicer and they call it a cemetery state. Yeah, but it's a state where once you enter it, you'll never accept, and you'll just read through the whole input and never do anything. And here, in the context of NFAs, it just means if you're in, let's say, Q2, Q3, and you read an A, then you can't go anywhere.
Is it kind of like an infinite loop, sort of?
It's not really an infinite loop. It's just saying in the original, so think NFAs for a second. It just means that if you happen to be in 2 or 3 with the symbol A to read, you cannot go anywhere, which is true. Q2 in the original NFA has no transition on A, and 3 has no transition on A. Okay? The whole procedure?
No, just explain what you're doing.
Yeah, so what I'm trying to do is model all the possibilities of states I could have been in the original NFA, because the DFA does not have nondeterminism. So I need to simulate, so this is a common theme we'll see many times. We'll try to simulate the possibilities that you could have been in, because in the NFA, I don't know what it's going to do. It's going to make some choices, but why not just model all possibilities at the same time? Okay, so like at the very beginning, I don't know which state the NFA would have gone to right at the start before reading anything, but I know it's either 0 or 1, Q0 or Q1, for sure. So I'm going to model all possible states I could have been in as the start state in the DFA. Okay, does that make any sense? You had a question?
Don't we get a final state?
Great question, I'll get right to that, but any other questions?
So I just want to be clear, the reason why the last state we created from Q2 on B can go to Q1 is because the transitions on B to Q0.
Yeah,
Q0
and
has the epsilon transition to Q1.
yeah,
And
so
that same logic applies for Q2 to Q3.
exactly.
Okay.
So the whole procedure we'll see soon is you make a transition first that is not an epsilon transition, then you figure out where you can go on epsilon transitions. Question?
Could you use the transition table to do this?
Yes, that you could, but people like state diagrams more instead of tables, so state diagrams are perfectly fine here. Any other questions? Yeah.
So we only go to a dead state if most of the state that we're looking at doesn't have a destination.
Yeah, on that particular symbol, yeah. Every state in this set has nowhere it could go on that one symbol.
If one of them does, then we write that.
Yes. So what we're going to do is, We're going to look at the set of possible states you can go to and union them all. Yeah, but any other questions? All right, cool. So we're ready to prove this result. Every language recognized by an NFA is regular. A language is regular implies it has a DFA. All right, so in informal terms, this means I'm converting an arbitrary NFA into a DFA. So, for that reason, let N with the 5 parts be an NFA. Okay. Well, if I want to show that the language of N is regular, what do I need to do? Show that there's an equivalent DFA with the exact same language as N does. So we construct a DFA D. So it's going to have different states. It has to have the same alphabet because it's the same language. It's definitely going to have a different transition function because the states changed. Different start state and different set of final states because the states change. And we'll do that as follows. So all I have to do is define the other 4 parts, Q prime, delta prime, Q0 prime, and F prime. And if I do that, then we're all rolling. So let's try to think, how are we going to design our DFA? So what we're going to do is, well, I have some sets of states in each of the 4 states that I just made for the DFA. If there are 4 states in the NFA, how many possible sets of states are there? 16. How do you know? Powerset. Could I, in general, have an NFA where the DFA may need all possible 2 to the n states? Yeah, I almost made that a homework problem, but there are examples of NFAs that require all 2 to the n states. But is there any discrimination against some of these states? Is Kansas a really bad state? No. But even if I don't need some of those states, is there any reason not to leave them in? Like if for some reason I didn't need that state right there, Q2, Q3, could I put it in anyway? Would that change anything? No. So since there are 2 to the n states via the power set, maybe what we can do is have the DFA be all the sets of states in the original NFA. Hence, it's called the power set construction. So this is just a colloquial term for the power set construction. So we're going to define Q prime to be the power set of Q. So this is just like the example we had above. We had some subsets of states, so each one of those, even the empty set, is an element of the power set of Q. And we were just modeling, if you happen to be one of the states in this subset and you read this particular symbol, what other states could you have gone to in the original NFA? Okay, so all we're doing is we're relating subsets of the states in the NFA to other subsets of states. Okay? So now we got to figure out how we're going to design the other parts, because it seems intuitively clear that we could just include all possible subsets of states, but then we got to figure out how we're going to design the transition function, how we're going to design the start state, final states, all of that stuff. So we're going to take a little bit of a detour before we come back. So, and then we're going to try to formalize the notion of these pesky epsilon transitions. So how did we know that Q0, Q1 would be the start state of the DFA? Yeah, there's an epsilon transition from the NFA start state to Q1, another state. If there happened to be another epsilon transition to maybe Q2, let's say, would I include Q2 as well?
Yes.
Yeah. So maybe I need to have a formal idea of all the states that you can go to via epsilon transitions alone. Okay? If you happen to be in Q0, let's say, the possible states you could go to are Q0, Q1, and if I added that one, Q2, via epsilon transitions only. Okay? So let's try to formalize that notion. So what we're going to define now is the epsilon closure sometimes written with the actual symbol. Should learn to spell closure of a set of states S, and we're going to call it capital E of S. So what we're going to think of this S thing, the set of states, is the states that you are currently possibly in the NFA that you could have gone to. And now what we need to figure out is where else could you go to via only epsilon transitions from those set of states S. Okay? So this is the smallest subset. I think I got that right. Yeah. X of Q, such that 1, S is a subset of X. Because if there happen to be no epsilon transitions from any of these states in S, then there's no reason that the epsilon closure of this is smaller than the set S that we already have right now. So it better be at least as large as the set that we're currently looking at. And 2, what we need to say here is that if you happen to have a transition, an epsilon transition from any state in S to any state that's currently not in S, then that state not currently in S is also now in S. Okay, so I'm just expanding the horizon until I can't go any further via only epsilon transitions.
One more time.
Yeah. So I'll do an example. So what we want here is that if we have a set of states that we're currently in right now, and there's a transition from one of the states in the set that we're currently looking at to somewhere outside of there as an epsilon transition, we'll include that state as well. Okay, does that make sense? Okay, cool. So how we're gonna say that is if a state is in X, so the states that we're going to have as our horizon, and let's see, how am I going to write this? No, I'm going to say that if T is another state such that if we go via this state S, via an epsilon transition to this state T, then what do I know is true about this state T? It better be an X as well. T is in X as well. So this is just a formal way of saying if you have a state that you're currently looking at and there's an epsilon transition to some other state, that state is in the set that you're looking at right now. And I want smallest subset here because I don't want, once I figure this out, to have some state way out here that I can't reach via epsilon transitions. Okay? So it better be the smallest subset here. And it better include the set of states that I'm already looking at. Any questions on epsilon closure? So I'll do an example. So if we come back to, let's not be barbaric. So what does the epsilon closure take in its as its argument? What is this S thing? A state or a set of states. All right. So what is the epsilon closure of the set Q0 here? Well, I'll go through it and then we'll work through the next one. So it's a smallest subset such that it contains this set Q0. So I must have Q0 in this set right now. But do I include anything else? Q1, because per the definition, if there is a state that's currently in the set that we're looking at with a epsilon transition that goes somewhere else, I now include that guy as well. And we don't have Q1 in our set, so I'm going to include it as well. And there's no other epsilon transition via these two states to anywhere else, so that is the epsilon closure. So this idea of closure is used a lot in mathematics, where you have some particular object that you're looking at, you apply closure to it, and you may get more things along with it. All right, so let's do one more. Epsilon closure of Q0, Q2. Well, what two things must be in this set? Q2 and Q0. Yep, it must include those things. What else must it have? Q1, and the reason is epsilon transition from Q0 to there. So I include Q1 as well. Anything else? Q3 for the same reason. There's a transition from 2 to 3 via epsilon only. So I include Q3. Okay? Is the idea of epsilon closure clear? Great. I haven't forgot about the question from earlier about the final states. So let's, before we completely do the definition of the construction, let's come back to the DFA that we were building. So let's suppose it's not true here. Let's suppose that I am finished with this DFA. We're completely done. Well, how do I mark what is final and what is not final?
Like anything that includes that final state is final.
Yeah, so what we're gonna see is that anything, so the only final state here is Q3. So which of these states will be final? The right two. And why is that true? Well, just because it has a final state in it does not mean that I should make it final. Why should I make them final? How does an NFA work? Right. If there is such a way for me to eventually accept, I will make the correct choice. So it says here that I could be in Q2 or Q3, right? I have the possibility of being in Q3 if I made the right choices. So that's why I should make it final, because the NFA, since there is a way for me to get to Q3, I should make that final, because the DFA does not have that choice like an NFA does. So informally, if the states that we're making have anything in common with the set of final states from the NFA, I should make it final. Okay? Is that clear? Okay. So let's finish up our thing. So I'm gonna copy and paste this down. Have I told you how much I love notability?
Yeah. The best one.
It's the best ever.
Doesn't have that.
All right. Well, we got to define the other three parts. I'm going to leave the transition function to last, as I always do. So let's do the start state next. Well, let's see. What state, well, here, what are states in the DFA representing in terms of the NFA? A set of states, right? So Q0 prime better be a set, right? Because they're representing sets of states in the original NFA. What must be in this set? What state must I put in there? Q0 from the NFA. So Q0 must be there no matter what, because I got to start at the same place that the NFA did. But what else do I need to include? Like in our example where we had that epsilon transition to Q1, and if there were other epsilon transitions, then we need to include those other states as well, right? Right. So how do I include those other states that I might go to? Epsilon closure. So I'm going to take the epsilon closure of this guy. So just like in our example from before, the epsilon closure was Q0, Q1, and that was it. And that's how we made the start state in the original DFA. Okay? In the DFA we made. All right. Let's do F next. What is F structurally? It's a set of states. So what do I better write? A set of states. All right? That's completely uncontroversial. So what are states in the DFA representing in terms of the original NFA? Sets of states. So I'm going to represent this as a set X as a subset of the states of the NFA here. So there's a reason I'm not representing this as a name of a state in the DFA. I'm representing this as a set of states in the NFA, which are states in the DFA. Okay, so it's all the subsets of states of the NFA here, but which ones did we make final? The ones that had something in common with the set of final states of the NFA, which is what? In general. F, right. So if X, this subset X, and F have anything in common, then I should mark X as a final state. How do I check if two sets have anything in common? Intersection. And if they have anything in common, what do I know about the result? Is it empty or is it not? It's not empty because it's intersection. They're in both of the sets. So X intersect F, so this should be F prime at the beginning, sorry. X intersect F is not empty. Okay? So let's recap. I'm going to look at every single one of the states in the DFA, and I'm going to look at it as a set. I'm going to look at all the states in the set of final states of the original NFA, and if any of them have anything in common with this set, then I'm going to mark that state in the DFA as final. Because that's just what our notion of how we made a state final in the DFA. We'll do examples, I promise. But that is our intuition, that was our intuition when we made the DFA in terms of what we marked as final because of how non-determinism works. Okay? Does that make any sense? One person said yes, so therefore everyone says yes. We'll do examples, I promise. Did I leave anything out? Transition function. All right. Hold on to your hats. What does the transition of a function of a DFA take as input? A state and a input symbol. What are states in DFA representing in terms of the NFA? Sets of states. So I'm going to write this as a state called S, but it represents a set of states in the NFA. Okay. So let's think about what we did in the original NFA to DFA from before. How did we know? Let's look at Q0, Q1 on the input A. How did we know that it was Q2, Q3? So what did we do with Q0 first? We said, where did it go on input A? First. What did Q0 do on A? Nothing. So that is the empty set of states. 0 states. Then we said, Q1, where could you go on A? Q2 and Q3. So we look at the set of states you could have went to with Q1, and what did we do with the empty set from Q0? We unioned them together. If we did the same, we're not, but if we did the same for the state in the lower right, 0, 2, 1, 3, what would we do on input A? We would see what Q0 did on A, Q1 did on an A, Q2 on A, Q3 on A, and what would we do with these 4 results? Union them together. So we'll start off at that. So we're going to come down here. So we're going to take a gigantic union over every little state in this big set of states of the NFA. And then we're going to ask, what did the original NFA do on input A from this little state S? How can I find that out? Transition function of the NFA that was given. And that was called delta. So we're going to look at delta of little s, comma, A. And then just combine the results together. So look at every single one, union all the sets together, and then that's the set of states that I could reach. Okay? We're not done yet. What did I fail to mention? So let's see. We forgot to include the epsilon transitions, right? So if I happen to be in, so what's a good example? So let's look at Q2, Q3 on input B. So when we came down to the set of 4 states. We said, well, Q2 goes to Q0 and Q2 on input B, and Q3 goes nowhere. So the set we're currently looking at is Q0 and Q2. How did we put Q1 and Q3 in there? Epsilon closure. So we just need to take the epsilon closure of this thing. So take the epsilon closure of that guy. So let's recap. In the DFA, we're just going to model all possibilities of states that we could go to. We're going to model all possibilities of states that we can go to, and that's just the power set of Q. We had this idea of epsilon closure, which just means go everywhere you possibly can from where you currently could be, and then include those as well, because the DFA does not have epsilon transitions. The final states are just the ones that have anything in common with the original set of final states, because that's how nondeterminism works. And the transition function says, well, from the set of states you're currently possibly in, figure out where you could have gone on each one of them, put all the results together, and then figure out where else could you go on epsilon transitions. Yeah. Yeah, so this is for all symbols A and S and Q. So because the DFA's function is total. Yeah, so I have to do this for every symbol and every state because the DFA's function is total. Okay? But any questions about this? Let's do an example. And conveniently, we have one. So let's see if I can do this in one swoop. So oopsie. All right, so I'm going to copy and paste our current example in. So we have 4 states so far. How many may I possibly need? 16 in general. So do you think I want to draw all 16 states? No, no one does. In general, I may not need all to the, yeah, go ahead.
How did you get 16?
16, because the original NFA had 4 states. And in the Powerset construction, we said that the DFA states will be the power set of the states of the NFA. And if you have 4 elements in a set, the power set of that is 2 to the number of elements, which is 4, so 16. But I may not need all of them, and I believe in this example we won't need all of them. So a method that I'm gonna, so you could use all to the n, but I think that's not gonna be really helpful in general. So what I'm gonna suggest is this idea of building the states as you need them. So if we build only the states that we need and not the ones we don't need, then we still don't change the language. Because if I can't reach those guys, then I'm never going to need to use them. Okay? You could build all of them, but I'm going to suggest this way is better. So we're kind of along our way here. We have those 4 states. So we finished Q0, Q1. Let's unmark this as final for now. And this one is unfinal for now. Q0, Q1 on input A goes to 2 and 3. We figured out we're A and B from the top 2 states, so we're done with those. The empty set state, we finished both transitions on that guy. So the only state we need to work on is 0, 1, 2, 3. So let's see. Where could I go on the symbol A from 0, 1, 2, 3? Well, let's see. Q0 goes nowhere. Forget about it. Q1, where can I go?
Q2.
2 and 3. All right. Q1 on, did I do that one? Yeah, we did that one. Q2 on A, where can I go? Nowhere. Easy. Q3 on A, where do I go? Nowhere. So the current set of states I could be looking at is 2 and 3. Now what do I do? Check epsilon closure. Can I go anywhere else via epsilon? From those 2 states? No. Oh, do I have a state already called 2, 3? Yes. Conveniently. So I come back on A. Now let's figure out where we go on B. 0 on B? Nowhere. Forget about it. 1 on B? Nowhere. Forget. 2 on B.
2 and 0.
2 and 2. Let's see. I'll hold on to that thought. Q0 and Q2. Should I include Q3 yet? No. So the idea here is figure out where you go on the actual reading transitions first, then you do epsilon closure. Okay? So Q2 on B only goes to Q0 and Q2. We will include Q3 in a bit, but it doesn't go anywhere else. Where does Q3 go on B?
No.
Nowhere. All right, so the current states I can go to are 0 and 2. Now what do I do? Epsilon closure. What is the epsilon closure of Q0 and Q2? Every state. Oh, do I have a state already called 0, 1, 2, 3? I already have it. So what is that now? Self-loop. Do I have any more states that I need to build? Nope, because every single one of these 4 states has a transition on A and B. And so therefore I don't need any more states to build. I think I like this idea a lot better than building 16 states. What happened to the other 12 states? They're not reachable from the start state. And since they're unreachable, I don't need them. I could build them, but I won't need them. Okay, so am I done building this DFA? Nope, final states. How do I find what's a final state and what isn't? Anything that has Q3, because that's the only final state in the original DFA. So this first state, Q0, Q1, no final state. Empty set in the lower left, no final. 2, 3? Yes, because that happens to have a Q3 in it. What about the one in the lower right? Yes. Does anyone know what language this is? So what must the string start with? It starts with A. And what? Well, it could end with an A in the case I go from that 4-state final state to the 2-state one. What substring can it not have? 2 A's in a row. And does not have the substring. I didn't even know that until I just saw this DFA, which is pretty cool. Does anyone see a problem with that description, or what may cause problems? If I happen to ask you, build a DFA that recognizes the language, starts with A and does not have the substring AA. Yeah, that's also true. Yeah, or is of the form A B star. A followed by any number of B's. Actually, no, that's not true either. There's still more strings in here. Do you see a problem with that description? It's becoming really complicated, right? Wouldn't it be nice if we had some formal way of describing the regular languages instead of making a machine model, making an actual description of regular languages? So that's what we're going to see right after the break. So let's take a 5-minute break.